why is the same model class able to memorize and yet generalize? We have 100,000 data points, 1.8 million parameter network. We should see overfitting, right? So the question now changes to why do deep networks have this implicit bias? So again, we've traced that deep networks don't overfit, and they don't overfit because they explore simpler solutions first. There is multiple ways to explain a distribution. Prefer simpler solution. What if we reduce 100,000 data points to just 100 points and keep the model the same? You can move around in that landscape without impacting the training error. For many parameters, it really doesn't matter what you set them as. You still have a good training accuracy. It's just completely crazy and surprising and very useful. I'm very excited to share whatever intuitions I have developed over last, let's say, 1 year. I started diving deep into AI about a year back, and incidentally it's been a year since Lossfunk, which was previously called Turing Stream, has been started. Started very small. We had an office, I think 1/10 this size nearby this, and we used to have very private talks. So gradually we started expanding, and I'm so happy to see all of you come here. And frankly, the whole motivation for doing this is because we were missing a community where you could discuss things like these. So there's lots of events, lots of communities discussing startups around AI, but very few communities where people go very deep into their curiosity rabbit hole and explore things related to deep learning to a lot of extent. So with that background, let's start today's talk. And today's talk is really about why does deep learning work so well. And I'm Chopra, founder of Lossfunk. So classic machine learning presents us with these intuitions. And I think the classic result in classic machine learning is about this bias variance trade-off. So if you have some data and a model, you can have these 3 different scenarios according to machine learning. You can have, on the left, you see overfitting. Overfitting is when you have significantly more parameters than the data points, so that your model remembers all the data points. And in the middle, you have this underfitting, where you have a really simple model. You have more data points and the model struggles to really explain what's happening in the data. And then in the middle you have good balance. So bias variance trade-off, just a 10-second summary of it, is what happens where bias is where you're injecting model's own bias into how the explanation of data is to be. So for example, underfitting is a classic example of bias being dominant, wherein if you have a linear model with a few parameters, you'll simply have just a straight line. But if the data doesn't follow the straight line, the model hypothesis space is not big enough to do anything else. So the key intuition in machine learning is that model hypothesis space is what restricts what the model is ultimately able to do. And on the right, overfitting is classic, where it has perfect accuracy on training data because you have too many parameters. But this wiggle that you see is where the test accuracy gets destroyed. So if your training distribution is, for example, very nice U-curve, and you have a highly parameterized model, then your model will be able to explain everything in the training data because it has too many parameters, it remembers everything. But between those training parameters, the model wiggles very widely, as you can see in the bottom. This is the, do we have a laser here? How does it work? This thing, red?
Yeah.
Okay, yeah. So this is the thing that you see where it's wiggling so much. And so if you're trying to predict on a data point that doesn't exist in the training data set, the model is just wildly mispredicting. So this has led to the ML best practices that we all have come to know. You divide your data into training, validation, test set, and you select multiple model classes like random forest, SVM, MLP. Within a model class, you increase model complexity. So you effectively just test, you fit models on you fit lots of different variations of models on the training data set, and then you see which model is performing best on the test held out data set, and effectively that's how you choose the model. And this has been the classic machine learning intuitions. But this was true in classic ML. In deep learning, this no longer holds true, and the objective of this talk is to explain why is that the case. So let's train a heavily parameterized network. So as you can see, we generate 100,000 data points from this function. You can see the function on the right. It has the true function is in red, but you sample points with some noise, and they are in blue behind it. And you sample 100k data points from this function that you see on the screen. And you then have a 1.8 million parameter network. So you can see this is a neural network. The total parameters are 1.8 million, and it is 18 times larger than the data. According to traditional machine learning theory, what we've all seen, this should overfit. And overfitting really means, as you saw in the bias variance kind of graph, what should happen with overfitting really is that your training error should keep coming down, but because it's overfitting, your test error should go up, right? That's the intuition we get from machine learning. So let's see whether what happens. We have 100,000 data points, 1.8 million parameter network. We should see overfitting, right? So what happens is this, it really doesn't. If you see, this blue is train loss and this red is test loss, both of them reduce. You do not see what you expect, that the 18x larger model, of course you should expect the train loss to go down. You have an 18x larger model, it should remember all the data points. 100,000 data points should be rememberable by a 1.8 million model. But what's more surprising is that this test loss is also very low. The test loss really doesn't increase, and that's what you should expect. And if you see the predictions from this 18x larger model, and this is all for test data, the model has never seen this. This is the test data points. If you zoom in around x, an extreme zoom around x, like literally, you see that the model is very smoothly interpolating. The model is not going like in wiggles, which is the classic symptom of overfitting. And this is an 18x larger model. And that's a surprising bit about deep learning, that it's just not overfitting the data when we expect it to do so. So another crazy experiment, what if we reduce 100,000 data points to just 100 points and keep the model the same as 1.8 million parameter model? It's an 18,000 bigger model. Surely it should overfit, right? Who thinks it should overfit? Okay. And overfitting means the test loss should go up, right? Okay, let's see what happens. Yeah. So this is what happens, the test loss. The red one. And again, just imagine this is just 100 data points, not even 100,000 data points. And the model is almost 2 million parameters. It's just completely crazy and surprising and very useful. And you can see also, you can't see it too clearly on this screen, but these are test data points that model never saw. And you see how the model is performing on those. So the upshot so far is really that modern deep learning networks do not overfit. It is a wrong intuition that we all carry from our pre-deep learning learning, from the whole classic machine learning theory. It just doesn't work at all. And this was a very nice paper in Europe's, I think 2018, where what they did was, if you remember the first, if you've ever done machine learning course, you start with these UCI machine learning repository datasets. These are iris, flower prediction, and these are datasets with just 100, 200 data points. Very, very simple datasets where you apply SVM or even linear regression and so on. That's how machine learning starts with. And they apply, modern neural networks on this. And they show that even in this setting, deep neural networks are capable of achieving superior classification accuracy without overfitting. So again, yeah, you have a question?
Is it just a change in architecture, or is it increasing compute? What exactly is providing?
That's the whole talk about. The whole talk is about what's driving this capability of deep networks to not overfit. So you can drive training error to 0, and yet test error doesn't increase. It can plateau, but it doesn't increase, and that's the intuition that comes from so many papers as you go down in this theory. So why doesn't deep network overfit the data distribution even if you have small data points, to answer your question? And I think to answer this, you should ask, what is overfitting anyway? Overfitting is when, as I said earlier, overfitting is when your model memorizes the training data and wiggles widely between those training data sets, which leads to bad performance in test data. And the interesting bit is that deep networks are capable of memorizing even random labels. So there was a very interesting paper where what they did was they took ImageNet and they just randomly shuffled the labels of images and classes. So no longer a cat corresponded to a cat, it corresponded to whatever else label. And deep network learned all of this randomly shuffled data. So, and I think it should. So it just reinforces the same point that deep networks are capable of perfectly memorizing your training data set. Even if you throw it a random data set with shuffled samples, it would learn it. So when trained over a completely random labeling of true data, neural networks achieve training error. So it is capable to get 0 training error on your training runs. That's just very true. If you have fewer data points and number of parameters in the network, it's very easy to drive training error to 0. But what's interesting is that the same network, the same architecture also learns very well to perform on the test set. So this is a proof. If you see, in this paper they do increasing level of label corruption. So if you have 100% of data set, here they will randomly shuffle 100% of the data, but here they are shuffling, let's say 0%, which is no shuffling. And in this case, obviously we all know that the test error is very, very low. So, I mean, you can derive this insight from what you see is that you have the same model class that's capable of memorizing your training data set, but the same model class is capable of generalizing really well also. And interestingly, if you see the linear increase in the test error, one of additional insight you can derive this from this chart is that deep networks are capable of extracting any statistical signal from the data. If you have, let's say, on a continuum 0 to 100 statistical signal where 0 is perfect noise to 100 is perfect signal, you can just vary this continuum in your data to whatever level, and deep networks will extract whatever signal they can find as evidenced by their performance on test data sets, and I find that really beautiful.
Yeah. What is should be?
It's just percentage of samples you've randomly shuffled. And test error means on the held out test. Of course, if you randomly shuffle all the labels on the test data set, the performance will be 0 because you've not shuffled that on the test data set. But if you don't shuffle anything, the performance is really good on the data that the network has never seen before.
It's all about shuffling.
What's all about shuffling?
It's all about shuffling, guys.
What do you mean by that?
The level, shuffle the level and
For example, if you shuffle all the labels, obviously you won't get any test set performance, even though the model has memorized everything. But if you shuffle none of it, you have excellent test set performance. This just shows the increasing number of shuffling you have, the test performance changes correspondingly.
Okay.
So the network is just extracting whatever juice it can extract from the patterns. Yeah.
You'll be shuffling the test data or something? Yes.
No, you're not shuffling the test data. Test data is just there to see. Imagine you're shuffling different amounts of your training data set, and then you're measuring on the test data set their performance.
So the statement really is this, that the shuffle part won't confuse the model. It will do very well for the unshuffled part.
Yeah.
And the shuffle part will just be clean.
The shuffled part, but the interesting bit is the shuffled part, the model will remember it because the training error is going to 0. But the unshuffled part will contribute to the model learning patterns that it helps perform on the test set.
Another thing is that because both of that thing is very almost linear, as if I just got activities at the initial rate components. So as much as the corruption is happening, like the test value is increasing by more or less.
Yeah, that's interesting bit. That if you have 20% corruption, your performance only worsens by 20%. So model is just hungry for any pattern it can seek. Okay, so let's move on. So how do you explain this? That's a big question. Any guesses? I mean, of course, I'll go through multiple intuitions I've developed, but what's happening? Why is the same model class able to memorize and yet generalize? Okay. Awesome. So reason number one, and there are multiple reasons. There's no single answer, but this is the first intuition is about that deep networks are capable of overfitting, but they tend to explore simpler solutions and hypotheses first. So, sorry, yeah.
This is conditional to soft inductive bias, like.
Yeah, this is a soft inductive bias. So one way to understand,
One thought that I got, why it memorizes the random labels, probably because there are not enough data points of those random labels, right? Like for consistent data, there is considerable amount of data for it to simplify it and find the patterns, but then generalize it. But then for random shuffled ones, there are not enough data points, so it memorizes probably.
But then the question is, why is the generalized one insector constraint? That is the main question.
yeah, why not? I mean, then it should not perform anything. I mean, you're just saying what happens, but why it happens is the interesting question. So the first reason why this happens, let's say, to reiterate the question, why is the same model able to memorize everything and yet extract generalized patterns when those patterns exist, is this thing that is called as soft inductive bias. So inductive bias is, I mean, you can think of inductive biases as things that you prime models with. For example, in convolution neural networks, you have an inductive bias that this translation invariance, where you can have cat anywhere in the image, but it will still detect the cat. In deep neural networks, the soft inductive bias is that the network should explore simpler hypotheses first before getting into very complicated hypotheses. We'll come to why that inductive bias exists, but this is the mental model you should keep in mind, that a deep network would tend to find first simpler solutions before getting into very complicated solution. And what simpler solution really mean, if you remember, if there is multiple ways to explain a distribution, if you have a U-shaped distribution, a complicated way to explain it is to go really wiggly, where you need a lot more effective parameters to describe that wiggly distribution, because it's just more complex. But neural networks, for some reason, no matter how many parameters you throw at it, it will always tend to first explore the simplest solutions. And if those simplest solutions don't work well, that's when they start exploring more and more complicated solutions. So for example, you can see, if you see in these diagrams, these are the hypothesis space for the model, and the inner ones are simpler solutions and the outer ones are more and more complicated solutions. The models start to first explore the simpler solutions, and then they do more and more complicated solutions. Compare this to uniform bias. Let's say if you don't have this soft inductive bias and you just have a very complex model space, then the model could start randomly anywhere and it could end up stumbling upon a solution that works really well for training data set, but it has stumbled upon such a complicated way to explain training data set that it doesn't generalize on test data set at all. So this is what's really happening. And but the interesting question here is to also ask, why do simpler solutions work better for test data set or not? Okay, so neural networks first explore simpler solutions, and simpler solutions and end up having good performance on training data set. But why do simpler solutions work well on test data set also? And I think that's to do with, and we'll come to that later, but really the intuition to that is that's to do with how our world is structured more than how models are. If you see the whole Occam's razor, most observations we see are explained by very simple reasons instead of very complicated reasons. But we can see a counterfactual world. In an alternative universe, things were way more complicated, and this wouldn't be true. If you have a model that works on and stumbles upon a simpler solution, in that counterfactual world, you would not have a good test performance, but we don't live in that world. Okay, so moving on, it's very interesting that this is not just restricted to deep networks. So this is a very good paper, I highly recommend reading it. It's called Deep Learning is Not So Mysterious or Different. In this paper, they also show that even a simple linear model can show this soft inductive bias. So what you see here is different model families. So one is degree 2 polynomial, one is degree 15 polynomial. So you can maybe forget about cosine right now, but let's say you have data generated through degree 15 polynomial, which is a very, I mean, if you know polynomials, it's let's say x square, x cube, x to the power 4 and so on and so forth. If there is data generated through degree 15 polynomial, it's very complicated. And if you have data generated through degree 2 polynomial, it's relatively simple. So what if you had a polynomial regression where you have a degree 15 polynomial fitting to degree 2 polynomial data, you would expect overfitting, right? Because you have 15 parameters and the data is generated through very simple means. And this is what happens. So if you see the test performance on degree 15 polynomial is very, very bad as compared to degree 2 polynomial. But there is another thing in green, which is degree 15th order polynomial, which has order dependent regularization. I'll talk about what this means, but you see its performance is exactly the same as degree 2. So this is a 15 degree order polynomial whose performance is same as degree 2 polynomial. What they do is that they simply have this order dependent regularization, which means that in the higher if you have a higher order of polynomial variable, you penalize its weight much more than lower order polynomials. So what happens implicitly is that the model fitting will start to explore simpler solutions first and only get to degree 15 if the data really deserves it. And you see this happening very interestingly. So the green is degree 15 order dependent regularization. It works well for data generated through degree 2 polynomial, but it also works really well for data generated through degree 15 polynomial also. So it's flexibly adapting to how complicated the data distribution is. Any questions? I know this is a little bit involved, but anything not clear, I'm happy to explain again.
What is the model that you use? It's a linear model.
Linear model?
Model trying to fit a
degree 2 and degree 15 polynomial. But just that in one case there is no regularization, so you are trying to learn weights of all 15 parameters. But in this you have an order dependent regularization where higher order variables are just penalized much more. So if you can explain away with few variables, you would. And that's why it's flexibly fitting to any complicated distribution. Okay, all clear? Yeah, sorry, you have a question.
On this, but I don't really soft inductive bias. And what is that?
So soft inductive bias here would mean that, so for example, a hard inductive bias would be something like convolution neural network, where you have these convolutions happening and it is either it's happening or not happening. It's sort of like a binary. You've coded it in. Soft inductive bias, it's their way of saying that we have preferences for what we prefer over other things. So it's not like the model will never fit a complicated distribution, but it just starts by exploring a simpler solution and then gets to a more complicated. It's not like, I mean, you could imagine a hard regularization like never go beyond 20 variables, for example, because it would be overfitting. But it's a very soft preference over what should happen.
But this doesn't, I mean, do they showcase anywhere any proof for this being the reason that happens in deep neural networks? I mean, deep learning methods?
I mean, showing proof about deep neural networks about anything is impossible. So you are, I mean, these are
intuitions of
like intuitions they are building. I mean, these are million parameter models. You'll always have a simpler model of this complicated beast. But they do talk about why this happens, and I'll walk through some of those things.
And do they show memorization as a after effect of this also? Meaning that time you had what extremely high degree per, right?
So if you have a data generated through degree 15 polynomial, then degree 15 polynomial model will fit perfectly to it, right? It has to.
Okay, yeah, for a 15.
Yeah. So effectively, I mean, deep neural networks are like piecewise linear models. So given enough parameters, they can fit any distribution to that granularity.
Exactly.
Yeah.
I mean, is this sort of generalization dependent on how heavy the soft inductive bias is? Which means if the bias is much lower, say, these order dependent regularization.
Of course, I mean, the bias is hard coded here, right? So you can literally change it, and the bias is just in front of your eyes. So it is dependent. If you penalize, if you have this value higher instead of, let's say, 0.01 square, if it was 0.5 square, then this performance will be worse because it would be much more scared, for lack of a better word, to increase the weight for higher order polynomials, right?
No, but now my question is that suppose we keep a very little, like you reduce the weight of that, make it much lower, so the bias is very, very little. Now if you train it for an extremely long amount of time, do you still think that the test loss will still decrease?
Yeah. And there are more reasons for that which are unrelated to this, but yes. The point is, the longer you treat, in fact there have been papers also that even if your loss has more or less plateaued, the longer you train, the better the generalization is. And the reason for that will become clear, but effectively to do that, in the loss landscape, the flat minima, what's it called as flat minima, where the test error is low, they occupy more volume than sharp minima, and the longer you run, the more chances that we'll get to a valley of that. Okay, so moving on. So the question now changes to, why do deep networks have this implicit bias? So again, we've traced that deep networks don't overfit, and they don't overfit because they explore simpler solutions first before getting to more complicated solutions. But then the question now translates to, why is this case? Why deep networks have this implicit bias towards simpler solutions? And I'll show a couple of intuitions for that. One intuition, the first intuition pump you can use for why deep networks explore simpler solutions or prefer simpler solutions is, you should imagine deep networks as to be ensembles of many, many models. So there is no such thing as a single model. Deep network is almost always an ensemble of just many models it has learnt from subsets of data point. So it goes right from, you may have heard of this lottery ticket hypothesis, where this hypothesis really is that when you have a deep network, there are just many sub-networks within that one network that are already primed to perform well on your training data, and the gradient descent simply ends up finding that sub-network that works really well. But here what you can also see is, you can imagine that because there's so many combinations of different circuits in a deep network, that you can think of what's happening is that different circuits are really voting for predictions. And just like, I mean, why does random forest work better than fitting just one decision tree? And anyone can give that answer?
You have multiple.
Yeah, so you have multiple decision trees that you're learning, and what ends up happening is that the average answer ends up being better because you remove the idiosyncrasies from the training data set. You only have, I mean, the whole wisdom of the crowds, right, where the outliers end up getting cancelled, and you see the same. So in this paper again, they fit deep neural networks on some circular data set, and you can see that different sub-networks, if you decompose a neural network, learn slightly different things. So when you ensemble them, you get just better test performance. Any questions on this? Should we move on? Yeah. This is all, I mean, it's both proven and a hypothesis. It's proven in a particular setting. Yeah, this is proven. This is not a hypothesis. So this figure is from this paper. But these are intuition pumps, because to say anything about a 500 billion parameter model, I don't think anyone can say anything clearly. You always have models of these models that you talk about, and these are just models that they've made. So yeah, remember the deep networks again have simpler hypothesis because they are ensembles, and ensembles are simpler hypothesis by design. And yeah, so interestingly, they do show that what a deep network ends up learning is very much like a random forest in this paper. So literally deep network in this case is replicating what random forest does. The second intuition pump is, and I think we stumbled as a community, maybe a bit empirically or randomly, but the interesting bit is that we end up initializing weights of a network with very small values. So all of us know Xavier initialization, where we set weights as very tiny values, and the side effect of this is that if the weights are very tiny, imagine almost all weights are contributing close to 0 at the start of the training run. And if gradient descent has no reason to change them, it doesn't change them significantly. So contribution becomes very, very little for a lot of weights, and this is what again DeepMind researcher says. He says that we initialize and optimize the deep networks in such a way that model explores simpler functions before complex ones. And interestingly, he says that although overfit functions exist in weight space, they are usually much harder to find. So in theory, you can set up weights of a deep network so that it ends up overfitting, and I think that's a very good exercise all of you should try. But it's very hard to get models to overfit. By design, they will just not tend to do it because the weights are so small, and gradient descent ends up only tweaking the few weights that it needs to, and those are usually simpler hypotheses.
That's on pause.
Intuition pump 3 is one reason why simpler hypotheses dominate is, and maybe I can spend a minute here, and please ask if something is not clear. You can think of what's happening here as a lost landscape. How many of you know or have come across lost landscape? Okay, so I mean almost all of you, but just to spend a little bit more time, is lost landscape is, imagine if you have a function where you have, let's say, 100 parameters in a model, and all 100 parameters you can vary, and as you vary you have a test error with each of those parameters. And what gradient descent is really doing is it's exploring this landscape. It's really exploring this question of what parameters should I set so that there is smaller and smaller error. In this case it's training error, not test error, because gradient descent doesn't have it. But the intuition really is that different kinds of lost landscapes have different generalization property. And to understand this is, you can see lost landscape of these two. Intuitively we can say this is better generalizable versus this. And the reason for this is because in this, and an interesting bit is that both of them have similar loss for the training data set, because we have loss only on the training. Their depth or the loss number is same, but yet their test error will be different. One is 7% test, the other is 100% test accuracy. And the reason for that is that if you have a more, what they call as flatter minima, it means that you can change weights of the network and you can move around in that landscape without impacting the training error at all. And this just means that your data set is not really getting impacted by change of the parameters. And if that's the case, the generalization is better because it means you have less wiggle. So for example, in this, if you move just a little bit, then your training error spikes, which means that there is just some crazy interpolation happening between your training data points, that even if you move just training data, these parameters a little bit, the model is performing so much worse. But here it just means that it's arrived at a point where for many parameters it really doesn't matter what you set them as. You still have a good training accuracy. So this is by definition a simpler hypothesis than this. Is that clear for everyone? Why spiky loss would have? And then the intuition really is that if you see the loss landscape, and this is proven in some papers also, wider minima are just more in volume than the sharper ones. And this is again a completely counterintuitive discovery, right? If you think of, let's say, a whole loss landscape as a cube, you would expect these wider minima to be much more numerous than these things. And if you are doing gradient descent in this cube, you're just much more likely to find yourself here. which would end up generalizing way better than this thing. So when I came across this, my mind was blown that this is an outcome of how lost landscapes are, and again, it could have been very possible that we had lost landscapes like this, but most lost landscapes are just full of flat minimas, and we are lucky that that's the case. Any questions there, or should I proceed? Yeah.
Do you have any impression why the lost landscape is tracked for deep learning networks compared to velvet networks? It makes sense that this is the thing that causes better generalization. So why is this there in the first place? Where it goes somewhere.
I think it's just tautological, right? If you wider lost landscapes would be much more likely.
Yeah. So in nature and for models, because both are acting on the same sort of physics. And quite you have simpler stuff and you can go on more complex things.
I think the question is, why do optimizers on deep networks end up finding themselves in these versus these? Because even in a polynomial model, loss landscape probably would be dominated by this. But it is possible that you get stuck in this, and I think the reason for this is this, which is the next slide, wherein if you have lots of parameters, there are always many directions for the optimizer to go down. I think we don't have a really good understanding of high dimensional spaces, but if you have billion parameter landscape, optimizer always finds a way to go down because there's so many paths. Because if you have 3 dimensions and there's a landscape, it's much harder to find. If you get stuck in a sharp minima, you get stuck because there is just mountains all around you. But if you have a billion dimensional landscape, I think there are papers also where they show with near certainty that you will find a way to go down, and the optimizer just goes down and you end up finding in a flatter kind of a minima yourself. So I think your question is correct. I think lost landscapes are a property of data and not the model. Of course the model parameters do signify it, but if you have, let's say, a 10 or 15 dimensional model, it's just more likely to get stuck somewhere in a local minima versus this, where deep networks optimizer never gets stuck in a local minima. It's also true, if you've ever seen that scaling curves, the loss just keeps going down. You just never see something like a plateau in most deep learning runs. Okay, so and I think this is the last intuition pump, also an interesting outcome of what we do with mini batch, or whenever we train on batches and we don't train on all the data, unlike classic machine learning. It's just that idiosyncrasies in the data also ends up cancelling. So imagine if some data is pulling up, the other data is pulling down. So just like you had ensembles of models within a deep network, you have this training data, the noise in training data being spread. And I think it's not true, it's also works in classic machine learning. Of course, if you train with whole data, it's also true. But also in deep networks, you end up just averaging out the noise due to this batch descent. Okay, so TLDR, deep networks can approximate any data distribution you throw in them. And the intuition really is that the magic is in the data, not the models. And early on, this was what image models did. If you asked picture of someone's back, they would put a face on top of it, because we have many more photos with people's faces than backs, and this is what happened. But of course, if any test data is out of distribution, the network will fail. So one of the mistakes as deep learning engineers we can do is have a separate training and test data, and if the right way is to have a distribution and then split it randomly. But what you can't do is, because deep networks are not designed for that, is have maybe train a network in arithmetic and test it on calculus or vice versa. Your distribution has to be similar for training and test data point, because they're just interpolating, they're not extrapolating. And what I mean by extrapolating is, if we see the natural data intuitively as humans, we know this will just continue, spiral. But this is a decision surface of a network, and the network is saying all this is just orange. It has never seen any data beyond this. And it's not modeling an underlying algorithm or the data generating process that we used here. It's simply interpolating between the data points that it's seen as a blue and an orange class. So it's a mistake to expect models to extrapolate when all they're designed to do is to interpolate the data they've seen in their training run. So deep learning, and in fact there's a very interesting paper also, I highly recommend reading this, Direct Fit to Nature and Evolutionary Perspective on Biological and Artificial Neural Networks. The authors say human brain is also doing the same. The evolution has primed us to interpolate and not really extrapolate, and this is a very good example of interpolation. And what they see neural networks are doing as an intuition, as opposed to overfitting and underfitting, is direct fitting. Fitting is when you have data points and you go through all data points, but you wiggle very widely between those data points. So if there is any unseen data point that you've not seen in the training distribution, your error is very high between this gray and the red one, because the model has no idea and it's just going crazy. It could be anything. But what's really happening in neural networks, and the authors say our brain also, we're very good at interpolating, where if we have seen two data points, we always do very simple linear interpolation between them. So there is no wiggles between it. And the reason we are able to perform the magic of reasoning is because most data actually is linear interpolatable. So whenever we make a decision based on our model, which is red, it's not too far from the actual distribution, which is the gray one. So again, the model, the magic is really in the data, not the architecture, not the science. Unfortunately, it's just fitting to lots of data points. And this I find very interesting, is because I'm reiterating this, is because magic is in the data. The data we observe lies on the smooth manifold, where if you've seen two things, the unseen thing we're able to predict, because things don't change that radically in nature. You see humans are more or less the same. You see patterns that you've observed in the past more or less the same. In a counterfactual world, things could have been very wildly, where this smooth interpolation between things could completely break down. But here we've seen with humans the radius of our eye pupils, heights, noses, for all of us is in a very certain simple range. So direct fitting from the samples we've observed is just very, very easy. And it's a property of the data and not the property of the data in the world we live in, and not the property of the model. And there is really no moat. This is why I think I was just reading Karpathy's tweet today, where they put models to have a random number generator, and all models say 27?
27, yeah.
27. So think about it, why should that be? That is because it's just modeling the distribution that's been fed to it. The parameters, the architectures really don't matter. If you have overparameterized model and you have lots of data and you have lots of computes, you put them in a cooker and you cook it, and you have a state-of-the-art model. That's the world we're living in, and that's what then it makes me introspect. Maybe that we as humans are also perhaps a little bit the same, where we attribute magic to reasoning, but the magic is really in these things, the flops provided by evolution and our calories, and the data we've seen, and the parameters in our brain. So let's take a moment to thank that our world follows certain rules, which generates predictable observations which are with learnable patterns. In a counterfactual world, things could have been completely chaotic. If you know no free lunch theorem, it says that there can be no general learning algorithm that performs equally well in all scenarios. And this is true also. You can create scenarios where deep networks fail completely, they don't end up learning, but those scenarios are completely useless because nobody wants to see them in a real world. Our real world is very simple, and we have these artificial masters now who just are very hungry to learn those patterns even beyond what we are able to learn. So thank you. I'll just close it here.